Collision. Collision is defined as the forceful physical interaction between two or more objects. It is the forceful, is the physical interaction between two or more objects. Yeah, most of the time, collision does not really involve three objects or four objects, usually two objects. But when we define, we like to say two or more objects, as there are some cases where it can be more than two objects. All right, that's collision. There are two main types of collision. There is inelastic collision and there is elastic collision. There is inelastic and there's elastic. Usually in collision, what we always talk about is momentum and energy, kinetic energy precisely. So in some cases in collision, we can have kinetic energy conserved or not conserved. But for all forms of collision, momentum is conserved. Don't forget that. It's a very important question. For all forms of collision, momentum is conserved. However, the kinetic energy might not be conserved or might be conserved. Now, in the case of inelastic, there are two subtypes. While for elastic, there are two subtypes as well. So what are the types of inelastic collision? There is perfectly inelastic collision. There is partly inelastic collision. While for elastic collision, there is perfectly elastic collision and there is super elastic collision. Some books call super elastic collision hyper elastic collision. The most appropriate name, however, is super elastic collision. So it can be perfectly inelastic, partly inelastic, perfectly elastic, or super elastic. What's the difference between these guys and what are examples under these categories? Now, for perfectly inelastic, what you observe in this case, first of all, understand that across board, momentum is conserved. Don't miss that anywhere. Don't get confused. It's not difficult. There's no issue there. Across board, in case you're asked tomorrow, momentum, kinetic energy with regards to elasticity, what can you say about them? Across board, momentum is conserved. The difference between them is not in their momentum, but rather in their kinetic energy. In the case of perfectly inelastic collision, what you observe is that in this case, there's no conservation of elastic energy at all, kinetic energy at all. Okay, let me give you examples and I will explain that again. Imagine you take, let's say, a sachet of water. You drop a sachet of water, it hit the ground. The sachet of water will not bounce back. It won't bounce, rather. It will move back, right? So in that case now, such collision between the sachet of water and the floor is inelastic, perfectly inelastic. All right? Or let's say you are eating, let's say satana, for example, or fufu, and it falls from your hand and hit the ground. It will not move back. It falls on the ground and stays there. That is perfectly inelastic collision. Now I have to use the example of fufu or satana. So those persons, or some persons that don't understand what I'm saying, or cannot relate it with sachet water. I don't know if there's anybody like that, but if you cannot relate to that, they can relate with fufu in the case of perfectly inelastic collision. In the case of partly inelastic collision, in this case, the object rebound, but does not rebound to as much extent as it was initially. See what I mean? Let's say I take a golf ball and I drop it down. If I take a golf ball and I release, take note of the position of my palm. If I drop the golf ball and it goes down, the golf ball will hit the ground. The golf ball will not return to this point. No, because energy will be lost. The golf ball will hit the ground and will probably return up to this point, and that will be it. If the golf ball is highly elastic, or let's say it's a football and it's highly elastic, it might just stop here. It might move up to this point, but it will never return to the original point, except you did not just drop the ball, you actually toss the ball. All right. So in that case, now the movement of a ball or the bouncing of a ball is an example of partly inelastic collision. So in this case, for kinetic energy not conserved, in this case, part of the energy is lost. In perfectly elastic collision, of course, no momentum is conserved across board, right? For perfectly elastic collision, what we observe is that the object will move downward, will hit the ground, and return back to where it was before. It will hit the surface and return back to where it was before. A perfect example of perfectly elastic collision is gas molecules. That's why if you check your chemistry textbook, you hear or you see where they say that the collision of gas molecules is perfectly elastic. So that's an example of perfectly elastic collision. While for superelastic collision, it will not just touch down and return, it will move way above that. And the classical example is explosion. So explosions fall under superelastic collision. All right, so this is all you need to know about collision that does not involve formula. The next part that we're going to talk about under collision is the formula representation. All right, for the collision formulas, there are 6 in number. 1, 2, 3, 4, 5, 6. These are not the formulas. These are representation of the formula. These are ways you discuss the formulas. When two objects, I'm discussing the first one now. When two objects moving in the same direction collide, all right? When two objects moving in the same, this is the same direction. This is opposite direction. When one guy is moving this way, the other is moving this way, that's opposite direction. When they are moving this way, same direction, same direction, same direction, same direction, all right? So when two objects moving in same direction, for some reason they collide, two things can happen. They can either collide and move apart, or they can collide and move joined together. Formula 1 is when they collide. Formula 1 is when they collide and they move apart. Formula 2 is when they collide and they move joined together. All right. So whenever they collide and move apart, this is the object. The first object moving in this direction, the second object moving in this direction. They collided. While the first object moved this way, second object moved this way. So it's like saying for the first object, it was moving this way. Let me use this to describe it now. They are moving this way, they hit each other, and they move this way, right? So for this first guy that moved this way, collided and moved this way, we can say why it was moving this way, it has mass and velocity, which give us initial momentum, right? Then after colliding with this guy, it moved this way, right? So now it also have mass and velocity, but now the velocity will not be final, meaning what you have here is final momentum. So initial momentum, final momentum. For this guy, initial momentum, final momentum. So I'll come out and say mu, not mumu, not mumu. Mu is for the first guy, mu is for the second guy, right? So I'll say m1u1 plus m2u2, meaning the initial, anything u means initial velocity, therefore it must stand for initial momentum. So m1u1 means the initial momentum of this guy plus the initial momentum of this guy. You understand now? The collision where they collide is always represented by equal to. So this is equal to m1v1 plus m2v2. All right. So m1v1, m2v2. So m1v1 and m1u1, it is what represent this way, while m2u2, m2v2, it is this part of the representation. So for questions where you are told that two bodies moving in same direction, when you hear the word same direction, think of plus. When you hear the word opposite direction, think what now? Minus. So for two bodies moving in the same direction that collided and move in the same direction but separately, the formula is given as this. You can jot that down based on what I've said now. For two bodies moving in same direction that collided and move in the same direction but separately, the formula is given as what you see now. While for two bodies moving in the same direction, take a look at this. This looks like this, right? This first part. That means if this look like this, therefore I'm going to use the same mathematical representation. So I'll come here and say m1u1 plus m2u2 equal to, why am I using m1u1 m2u2 in this case? Because take a look, what you have here is same as what you have here. So in this second case, what you have is two objects moving in the same direction that collided and move in the same direction, joined together. They did not separate. It's just like what you see in some movies. You notice that the protagonist and maybe the bad guy, the antagonist, many times when they are on a highway, they hit each other, as seen in some movies. They hit each other. There are times where they will separate and they'll go their separate ways. There are times where they will hit themselves, they will not move their separate way, they start moving together along the road surface. So whenever they separate, equation 1. When they join together, equation 2. So now come and see m1 plus m2 bracket v. Why? Because they are moving together, so they have a common velocity, they have the same speed. No one is moving faster than the other, they are moving together. So this is what you have. So whenever you hear the word common speed, common velocity, think of bracket and v. You understand? What about the third case? In this case, they are moving in opposite direction. They collided and they move in opposite direction. So what do you think the formula would be? You can pause this video and try and write it out. Have you done it now? Do you know the formula now for it? All right. So because they are moving in opposite direction, first off, I can't use plus. I have to use minus. And of course, they are moving. That means therefore they have momentum. So I'll come here and say M1U1 minus M2U2 equal to M1V1 minus M2V2. All right. M1U1, M2U2, M1V1, M2V2, minus everywhere because they move from opposite direction. They move in opposite direction. Collide and move in opposite direction. In this case now, they also move in opposite direction. But after colliding, take a look at this. I had to draw arrow here, and 1, 2, telling that 1 and 2 are now moving in the same direction. That's the reason why you have 1 and 2 here and you have 2 arrows. So in this case, I'll come out and say M1U1 for the first object plus or minus, right? Because they're in opposite direction, minus M2U2 is equal to M1 plus M2 bracket V. Why am I doing this? Oh, that's not difficult. Because if you observe what I did here, it's the same as what I did here. Take a look at this part. It's the same as what I have here. So if here is M1 plus M2 bracket V, then here should be M1 plus M2 bracket V. The next part now is when an object in motion collides with a stationary object. That's why you observe that in this case, there is no arrow. I didn't use any arrow to represent it because this guy is stationary, this guy is in motion. In this case now, I'll write M1U1, right? M1U1 for this guy. But this guy is stationary. We just said that. Whenever, if you watch the first video, I said something about this. Whenever an object is stationary, the momentum is what? 0, because the velocity is 0. So this becomes M1U1 plus 0 equal to, now check my presentation here. I have to use 1 and 2. The same arrow I used before is what I use now. 1 and 2, and there's arrow here. So you have this here that look like this, that look like this. If this is presented as this, and this is represented as this, then you know how this should be represented, right? So in this case now, this becomes M1 plus M2 bracket V. M1U1 plus 0 is still M1U1 minus 0 is still M1U1. So you can simply remove this from this part now. So you have just M1U1 equal to M1 plus M2 bracket V. And for the last equation, this involves a gun and bullet. Whenever the question involves a gun and bullet, or a bullet released from a gun, the formula expression is given as mgvg mbvb, where mg means mass of the gun, vg means velocity of the gun, mb and vb means mass of the bullet, velocity of the bullet, respectively. All right, so that is it. So from what we've discussed so far, which is equation 1, 2, 3, 4, 5, 6, you can see that whatever change you have in momentum before collision, it is always the same as change you have in momentum after collision. Now, this whole idea of what we've discussed, of everything we've said so far, of momentum itself, of impulse, of collision and all, even the formulas, they are all locked up in a law called the law of conservation of momentum. This law states that in an isolated or closed system, the total momentum before collision is equal to the total momentum after collision. The total momentum before collision is equal to total momentum. Total momentum before collision is equal to the total momentum after collision. What that means is that, let me use one example. In the case of a gun and a bullet, the mass of the gun, velocity of the gun, whatever you get here must be equal to the mass of the bullet and velocity of the bullet. We know that the velocity of a bullet is always more than the velocity of a gun, right? So if the v of a bullet is, let's say, 100, the v of the gun, for example, let's say it is 2. Therefore, the mass of the gun should be more than the mass of the bullet. The same way the velocity of the bullet is more than the velocity of the gun. That means if VB is 100 and VG is 2, if I say that MB, mass of the bullet, is 1, if I say MB is 1, therefore in this case now, the MG, must now be more than what you have here. 100 times 1 is 100. This guy now is 2. What must I place here to ensure that this guy will also be 100? 50, right? So this must be 50. So that 50 times 2 will also give us 100. So because this part is 100, this part is 2. 100 is 50 times larger than 2. That is why the mass of the gun is 50 times larger than mass of the bullet. Alright? 100, 2. Which is larger? 100, right? But how many times? 50 times. 100 over 2 is 50. So use 50 times, take big pass. This one use 50 times, take big pass this one. Now, why this one use 50 times, take big pass this one? So that after everything, the momentum for this part will be same as momentum for this part. So that in a nutshell, the law of conservation of momentum is obeyed. No energy is lost. Alright? No momentum is lost, rather. So that is it. We've gone through everything with regards to momentum, impulse, collision. So just go through these things. Watch the previous video. Watch this one and get a good understanding of it. Whatever you don't understand, no problem. Just drop the answer or drop the question in the comment section. Like, share, and subscribe. The videos will be helpful to you. I'm Dr. Olotu. As I always say, I'm here to help you deal with JAMB before JAMB deals with you. I'll see you in the next video.